All right, I am Gunnar Scott, and this is my concept teaching video for chapter 13.6 on the kinetic theory of the ideal gas. And the kinetic theory of the ideal gas kind of deals with this sort of model here. So imagine as if atoms in a gas are bouncing around at great speed in a confined space. So the distance between these atoms is great enough that we don't have to consider their interactions with each other unless they collide, as they are about to do right there. So, and they are colliding often with the surface of their confining space and with each other. And it is these collisions with the outside here, which is happening constantly all the time. Every wall is getting hit by these molecules constantly and bouncing back off in a different direction. It is these collisions that creates air pressure. So it's these rapid collisions that will keep your tire inflated, basically. And for simplicity, we assume that every collision here, either with each other or with the wall, is elastic. So talking about air pressure, let's talk about ideal gas and pressure. So the pressure a gas exerts on its surroundings is dependent on three things. So how many molecules there are, so how densely packed, how much gas is in this space, how often each of these molecules collides with a wall, and the momentum transferred with each collision, so how fast and how hard they're hitting these walls. And these all make sense. I mean, how many molecules are, more molecules means more collisions, which ties into the second thing that affects pressure, how many times they're hitting the wall. And then their momentum transfer each collision is actually dependent on several things, which we will talk about later, more temperature. But we talk about pressure, we can look at this equation here. So the pressure, the absolute pressure, times the volume is equal to the number of atoms or molecules times the absolute temperature. So that's kind of a way to simplify it down. And like I said, you'll notice that the force they hit, or the speed, isn't mentioned here, but it does mention temperature. So we'll talk about temperature real quick. So temperature, as most of you know, is basically the speed of the vibration of atoms. So this comes around to mean that the absolute temperature being in Kelvin, it's important to note. So if you want to find Kelvin, obviously just take Celsius and add 273. Just a quick note there, but the absolute temperature in Kelvin is directly proportional to the average translational kinetic energy of the gas. So if you were asked, how much does the translational kinetic energy increase from 50 Kelvin to 100 Kelvin? You would just say it doubles. It doubles because they're directly proportional, and the temperature is the main thing that affects it. Now, if you were asked to find the average kinetic translational energy in joules, not in Kelvin, you would want to plug the Kelvin in to this equation here. Now, KB in this scenario refers to Boltzmann's constant, and that will be 1.38 times 10 to the negative 23rd. Ooh. So pen's not working, but you heard me. 1.38 times 10 to the negative 23rd. So if you wanted to find the energy in joules, you would take 1.5 times 1.38 times 10 to the negative 23rd times your temperature in Kelvin. That's important to remember if you want that in joules. Now, another way to talk about speed as it relates to temperature in an ideal gas is to talk about the root square mean speed. So as root square mean might imply, you take the root of the average speed squared, and that is the root square mean. But more practically, if you're wanting to convert from average kinetic translational energy, or find root square mean with average kinetic translational energy, you're going to want to use this equation. So that is 2 times your average kinetic translational energy divided by the mass squared. Now when I talk about the mass, I mean the mass of one of these molecules. So say this was O2, Each one of these was O2. For this number then, you would want to take 15.999, or just 16, times it by 2, and then convert it to kilograms, because this number needs to be in kilograms. That's important. So to convert to kilograms, you would take your number and times it by, and times it by 1.66 times 10 to the negative 27. Sorry for that little step away, but I needed to find that number. So that's how you convert to kilograms. But the last thing we need to talk about with the kinetic theory of the ideal gas is the Maxwell-Boltzmann distribution. So the Maxwell-Boltzmann distribution deals with how many molecules have speeds in certain ranges rather than looking at the average speed of the whole gas area like these two do. So these different speed distributions are usually determined by different temperatures and are represented in curve graphs. So the reason that the Maxwell-Boltzmann distribution is important or is useful for practical applications is that it helps us understand planetary atmospheres. So different planets have different escape velocities based on their gravity. So in the upper atmosphere, if a molecule's velocity exceeds the escape velocity, it will fly out of the atmosphere. This is why lighter elements such as hydrogen and helium are less common in Earth's atmosphere, despite being very common universally. It's because they are light enough to fly out of the escape velocity and escape the atmosphere, which ties us back around into this. Temperature is not the only thing that affects velocity. The size of the molecule will actually slow it down. If it's a bigger molecule, it will slow down, which is why we take into account that right there. So lighter ones like hydrogen and helium fly out more easily out of the Earth's atmosphere. That's why the Earth's atmosphere is mostly nitrogen and other things. And that's why the moon's atmosphere has none. The moon has no atmosphere. It has such a low escape velocity that everything escapes. That's why it's important to mention the Maxwell-Boltzmann distribution, because it just kind of allows us to think about those kind of things. But yeah, just going over this stuff. So especially with temperature. So the temperature in Kelvin is directly proportional to the average kinetic translational energy. And then if you want that in joules, it is this equation. And then if you want that in root square mean, it is this equation. Remembering that Kb is Boltzmann's constant, and that is 1.38 times 10 to the negative 23rd. It's important to remember. And it's also important to remember that when you're converting the mass there, sorry for the noise, converting the mass there, you're going to want to find the atomic weight multiplied by the basically the chemical equation. So if it's C2, multiply the atomic weight of carbon by 2, and then multiply that by 1.66 times 10 to the negative 27th to get it in kilograms, because it needs to be in kilograms. So that's kind of what you need to know to talk about kinetic theory of ideal gas. Hope this has been helpful. I'm sorry if the video was kind of shaky or janky, or if I had to walk away to get some information. But I hope this helped, and I hope this will get you through the problems I'll have assigned for this.